Next up, I always wanted to do this. From the global industry reference for planning, design, and deployment of any Wi-Fi network, please welcome from not Siberia, but from Serbia, Vladan Jevremovic.
Well, thank you, Jussi, for your warm welcome. You'll just give me a few minutes until I set this up. Okay, so let's get started. The title of my talk is Stadium Design and Capacity Challenges. Just to clear one thing up, this is all from the RF planning and RF design perspective. I work for IBWave Solutions, and we are a software OEM. And our software product, IBWave Wi-Fi PC and IBWave Wi-Fi tablet, are really for RF planning and design. So we don't do any kind of field measurements after the installation. Having said that, let's get started. The agenda is quite busy. We'll cover a lot of ground here. We will start by talking about in-building propagation algorithms, and specifically two algorithms that are in use today. One is very well-known COST-231, and the other one is ray tracing. I'm fully aware that some of you have heard this part maybe 3 times, because I've spoken about it 3 times already at various conferences. So I have condensed this part to only a couple of slides, trying to get to the bottom of what is the difference between those two algorithms. And then we will go forward onto the good stuff. We will talk about some measurements that we have taken in a hockey arena and use that measurements to do a lot of fun stuff, such as compare prediction accuracy for those two propagation algorithms. We will also talk about calibration and whether that helps a lot or not much in particular for Wi-Fi deployment in a very dense deployments, such as arenas or stadiums, and apply that to the data that we already have. We'll be talking about inclined surfaces and the price you pay if you decide to forego proper modeling of inclined surfaces. And as you all know, in arenas and stadiums, this is something that is very important because they are, you can model the seating area as inclined surface. Then we will talk about fade margin. This is a topic that will be tied into the data that we have collected, and we will show what happens if you do not take fade margin into account. Finally, we will talk about directional antenna patterns, because directional antennas are used quite often in arenas and stadiums to isolate the areas, seating areas, into separate sectors. And then we will show what happens if you decide to use approximation of antenna pattern as opposed to the real measured 3D pattern. And in the end, what we will talk about is capacity, and we will show the example of how capacity can be calculated for a basketball arena. I will give you a specific example that will have a certain number of clients and the traffic that each client should support and the duration over which that traffic should be supported, et cetera, et cetera. In the end, what we will see is which AP and there are about 100 APs in there, can support this traffic and which one is failing and why. So let's get started. First, a few words about indoor propagation algorithms. The first one is a very simple one, COST 231. This is a direct path model that takes into account the distance between transmitter and receiver and all the obstacles in between, be that a floor penetration loss or a wall penetration loss. So all floors and all walls that are in between transmit and receive signal are taken into account. But that is the only signal, the only electromagnetic path, the only electromagnetic signal that is taken into account in this particular algorithm. We don't have any diffraction, no reflection, just a direct path in between transmit and receive. The good thing is this can be used in Excel spreadsheet by estimating the number and type of walls or obstacles that are in between. However, it works best if you can use CAD floor plan and if you can identify each wall and each obstacle with the material penetration loss database. This will automate the process of calculation and you will be more accurate. The good thing about this is it's simple, it's inexpensive, but it is unfortunately not very accurate for arenas and stadiums, as we will see later on. The second one is ray tracing, and this tells you what ray tracing is not. It is not a guy named Ray that is laying on the ground and we are using a chalk to draw a line around him. That's not ray tracing. Ray tracing is actually an algorithm that is using all possible rays, electromagnetic rays, between the transmit and receive, or AP and a client. And those can be direct path, and this laser is not really working well, but okay. Direct path, which is the red one, and then that direct path can be line of sight or a direct non-line of sight. Then we have reflected paths that are shown in light green, and they basically bounce off of walls and reflect off of walls and get from AP to client that way. And then finally, there is diffracted path that is shown in light blue. That is a ray that hits an edge, most likely an edge of a wall or a door, and bends around the corner to get into the client. So this obviously is much more detailed way to calculate what is happening out there in between transmit and receive radios. But unfortunately, it only works with CAD. So you have to have a floor plan CAD, and you have to have material penetration loss database. And so that right there makes it more complex than COST 31. And it is more accurate because you are taking more rays into account, but it is also more expensive. Expensive in the sense that it is computationally expensive. You have to use much more processing power to calculate a signal throughout the venue. But for this particular venue, that is a very complex 3D venue, such as arenas and stadiums, this is actually something that is much more promising, and we will then take a look later on to see what the accuracy is. So hockey arena, what we have here is a measurement that we have taken several years ago in a hockey arena at the cellular frequency of 2.1 gigahertz. And so the question then is, why am I showing you 2.1 gigahertz and not 2.4? Well, there are two reasons. The first one is this is close enough between 2.1 and 2.4. The second one is at cellular frequencies, the equipment that we have at our disposal is very accurate in the sense that it can be calibrated and it will give you repeatable results, which is to say if you have two receivers in your card at 2.1 gigahertz and you collect the data, once you do a proper post-processing, you should get very similar results. And that is not the case with USBs that we have at 2.4. Even from the same manufacturer, you will have a significant difference between two USBs, even though you were taking the data at the same time in almost the same location, which is from the two clients. So because we could not get repeatable results, we decided not to present them. And hopefully this will change soon. We heard that Ikahau is having Sidekick that has eliminated that problem, which is great news for this industry as a whole. So having said that, we basically are saying that at 2.1 and 2.4 are close enough that the measurements should be valid at 2.4, but the adjustment needs to be made. Typically in this very dense Wi-Fi deployment, your EIRP is not going to be 23 dBm, it will be around 0. So assumption was made that I have a transmit power of 0 and antenna gain of 3, so EIRP is 3 dBm. Now the minimum received signal strength is -86 because that's your threshold. Now I understand that it is very likely that at stadiums it will be much higher because of the ambient noise, but I will address that in a few slides. So this is the premise, and if you look at what we have here, you will notice that the path loss is vastly different. Path loss here for cellular measurements is very, very large, 118 dB. And this one is almost 30 dB less for Wi-Fi. So what I have done, and I wish I could point the laser there, but I can't, is that I basically cut off the data that we had at cellular frequencies. So what you are seeing here, the antenna all the way to the right and the data around it, it's just something that we have kept, and the rest that was going around the venue was taken off. So the prediction accuracy. Fast ray tracing. I told you about ray tracing. We call this fast ray tracing, and the okay, thank you. And we call this fast ray tracing because we just modified ray tracing to make it faster. So this is what you see on your left is fast ray tracing prediction, and COS31 is to the right. They look very different, as you can see, especially throughout in the back. And what we have done is, you see the data that we collected is right here, and we have a prediction, and then so what we do is we calculate the difference between the prediction and the measured data at the area where the points are. So this is a fair comparison. I'm not trying to find out how much different I am in this area, only in the area where I actually do have the data. And I don't know if you can see this, but the results are vastly different. For ray tracing, my absolute mean error is about 3.5 dB, and my standard deviation is about 4.5, whereas it is over 10 dB for either at COS231. That is very significant difference. And then, so the next question is, okay, but you guys do remember that I told you that the minimum signal is -86. So in practical deployments, it is not likely that I will have that as a target value. Most likely I will have something that is a bit higher because stadiums and arenas have a lot of background noise. So my next step was to take a look at the data and plot the error, the absolute error versus the distance. And then what I wanted to see is how that error varies with the distance. Because if you plan to have much more dense AP deployment, then what's going to happen, you are not going to be interested to see what is happening 50 meters away from the AP. Maybe you will be interested to know what's happening 30 meters away from the AP. So that was the next thing that we did. We actually plotted the scatter plot for fast ray tracing and for COS231, and we plotted the absolute error in dBs versus the distance. So I know that These two graphs look scary at first, but I will walk you through this to understand what is it that we are seeing here. First of all, if you look from the distance from 0 to 60 meters, which is what you will have if you put your EIRP at 3 dBm and your signal strength at -86, you will get the distance of 60 meters. So that is the full distance. And you see that this particular plot of ray tracing varies between 0 and 10 and 0 and 60 meters, but it varies, how would I say, you will see the delta that jumps up and down. It is not like I had like a 2 or 3 dB up until I'm 20 meters away, and then all of a sudden I started seeing those jumping up. So this is kind of like homogeneous distribution. What you see here is a line that approximates this behavior. Basically is telling you that you at 0 or 1 meter, your absolute error is about 3, and 60 meters away, it is about 4 dB. Pretty much is telling you that as you go further away from the antenna, you don't really experience significantly higher error. That is what this thing here is telling you. On the other hand, COS31 is basically telling you it goes from 0 to 70 dB. But if you look into that from 0 to 10 here, it is very compact up until you're about 22, 23 meters away from the antenna. And then you start seeing those large errors. So what this is telling you is up until about 25 dB, you have between 0 and 10 dB homogeneous distribution of error, which is very similar to what ray tracing is telling you. So why is this significant? Well, if you are designing for capacity, you may want to look into what the number of APs that you're going to have roughly, and if the distance between them is comparable to what I just said here. Because if it is, then maybe ray tracing would be good enough for you. If it is not the case, if you have areas when ray tracing has to be something like 30 meters away from each other or 40 or something like that, then most likely you will have to have ray tracing as your choice of the algorithm. So having said that, one last thing that I want to tell you about this is because of this large error here, you see that error steadily climbs between 0 and 60 meters. So that basically is telling you that this is much more sensitive to distance when it comes to judging the error that you make than this algorithm right here. So this one almost linearly goes up as you go further away, and this one kind of stays constant. Now, so we look into calibration as a way of helping with accuracy. So what is calibration? I'm going to go and collect the data in RF survey, and I may run the same path twice. I will take one set of data for calibration, and I will take the second data for validation, and then I will have this propagation path calibrated, which then can be applied to AP that is going to be transmitting in that area. So it takes time to do this, not in the sense to post-process the data, but to actually physically conduct RF survey twice. You're doing it twice because you have to have two sets of data. You cannot have one. One is for validation and one for calibration. They cannot be the same. So yes, you will invest more time into it, and hopefully you will get better accuracy. Actually, let's take a look at what is going on here. As this stadium design, as I said, has few specifics. First, the range of an AP is short. Why is it short? It is because usually we have ambient noise, which is high, which translates into high target client receive power. And then we also will have to have low AP transmit power, because if there are many of them, then you do not want them to have a very large coverage area. So what does it mean? It means that APs will be mostly in line of sight with clients. Okay, so I'm in line of sight with my client. It is a short range, so what exactly does it mean? It means that it is better default prediction accuracy in our tool. And it means that calibration will bring limited improvement. How limited? Well, maybe it will improve depending on the configuration, and depending on what you have in front of you. It may be 0.5, maybe 1 dB, maybe 1.5. But the bottom line is, if it is short range and line of sight, then if that is the case, you actually may be better off by not doing calibration, because your return of investment is going to be marginal. So how do you know? Typically, you do not want to take the data and then do the post-processing and calibrate and then see that there is half a dB improvement. You would want to know that beforehand. So how do you want to do that? Well, luckily in our tool, you can run something called nature of the path. So this is the antenna. And if I run this nature of path, it will tell me what's going on around the antenna. It's going to tell me how many pixels are going to be in direct line of sight, which is dark blue. How many of them would be diffracted, which are green. What would be direct non-line of sight, which is red. And what would be reflected waves. And so if you look into what we have, look at the data that was collected, and you will see the data nearby is in line of sight. So if this is going to be your AP range, then my recommendation would be don't calibrate. You are going to be good with default accuracy, at least in our tool. So that will save you some time in post-processing your survey data. So inclined surface. So how important is it to correctly model a surface? Here in this example, I did not take necessarily arena, but I took an escalator, which you can probably find in an arena or in a stadium. So there, as you see at the bottom of an escalator, there is an AP. And then, so if I have a horizontal surface, if I model escalator as a horizontal surface, and this is an escalator that goes between two levels in a subway station, in a metro station. So if I do that, then because I have AP around the corner, I'm going to have a decent signal. But if I actually do that as an inclined surface, then the signal is all dark. And the difference is about 20 dB. So obviously, you are going to model inclined surface in a stadium because the seating area has to be modeled as inclined surface. But it takes time to do that. And if you don't do that everywhere where it should be, including escalators, then the penalty you pay may be 20 dB signal difference. The next topic is fade margin. So I skipped the portion about fast fading margin. Well, there are two margins, slow fading and fast fading. And I will explain to you what the difference is. Fast fading margin is basically about multipath. And slow fading is about obstacles between transmit and receive, transmitter and receiver. Fast fading exists even if you are indoors and even if your client is not moving. It is just that indoors, if the client is not moving, which is the case in arena and stadiums, the effect of fast fading to the signal is not that big. So if you have a modeling tool, if you have a propagation tool, RF planning tool, then it's okay to say that the fast fading is equal to 0 dB. It will not affect you much, especially if the venue is basketball arena or a hockey arena or a football stadium. However, the slow fading is a different story altogether, okay? Slow fading exists always and always impacts your data, your prediction. And to understand that is that the prediction tools typically, what they do is they will give you what they call median path loss prediction. So what does it exactly mean, the median path loss prediction? Let's say that you have done prediction and you have said that this area right here is an area where your received signal strength is greater than some target value, let's say neg 70 dBm. And so the question is, what is happening at the edge of the coverage? And if I only go with median path loss, then what's going to happen is that if I walk around this edge and start collecting the data, half of my collected data will actually be less than this target signal level, and the other half will be greater. This is statistically speaking. So if I want to be better than that, because this is really not acceptable, because when somebody says, well, here is my prediction, you kind of expect that to be true in almost all the cases, not in half of the cases, which will be the case right here. And then basically what you do then is go and add slow fading margin. And if you add slow fading margin where 75% of the measured signal at the edge, cell edge, would be greater than your target area, then your coverage will shrink a little bit, which is the blue line here. And you can do one better. You can actually go in and add a greater slow fading margin where 90% of the measured signal at the edge of this coverage at the cell edge will be greater than neg 70 dBm or whatever target signal is. So as you see, as your fading margin increases, your probability that your measured signal at the cell edge will be greater than the target increases, but your coverage shrinks. And that's the price that you pay for taking into account slow fading margin. You are more confident that your design is good, but you basically need to put more APs in there. So how much slow fading margin is needed? So if you go into the literature, you will get some values. They will tell you for indoors, it may be, they measured 8 dB or 10 dB or something like that. Well, what we have done, we have measured this at that same hockey arena. And take into account that we have shrunk the coverage a bit, which means that I have line of sight mostly between my AP and my client. So what does it mean? The variation of the signal is not going to be that much. I'm saying this at the same time, I'm telling you that we measured 6 dB standard deviation. So you may think that 6 dB is quite a bit. Yes, it is, but keep in mind it would have been much bigger if I had allowed that path loss to be 118 dB, which was what we did for the cellular frequency. So we shrunk that path loss, and that's what we get, 6 dB. If I had assumed that my maximum received signal strength should be not neg 86, but maybe neg 70, this standard deviation would be even less. So what I'm telling you is that standard deviation is a function of your path loss and whether you are in line of sight or not. So for this example, we assumed that, very generic case for Wi-Fi at 2.4 at stadiums, meaning target signal is neg 86, transmit is 3 EIRP. Having said that, standard deviation is 6, cell edge reliability with 75% confidence is 4 dB, and with 90% confidence is 8 dB. It means that you need to subtract 8 dB from, you need to add 8 dB to your path loss. And then, having said that, this is how this hockey arena coverage would look like without margin, which is basically 50% confidence at the cell edge, and with margin, which is when I add 8 dB margin. Obviously, it is much hotter without margin, and with margin, this whole coverage looks much more yellow than red. But that's the price that you pay for being more confident in your design. Now, the next topic is antenna patterns. So here is what's happening. We have had actually customers come to us and tell us that they are not happy with the antenna radiation pattern when they're doing design for stadiums. Then keep in mind, this is cellular frequency, not Wi-Fi. So what we actually have had is OEMs, antenna OEMs came to us and said, okay, well, now we have 3D measurement patterns for our antennas, and we would like to put that in your database. So what you see is, on the left-hand side, is how a interpolated from 2D cuts antenna would look like. And this is how it would look like at 2.4. And I'm going to now switch to our software to show you how it looks in 3D. Okay, so this is 3D, and as you see, this is the interpolation, and you can choose the frequencies. You have 2.4, but there are lower frequencies as well. And so, as you are seeing, is in this area here, because of the interpolation, all those side lobes do not look very natural. And interpolation that we did was interpolation based on 2D cuts. You have vertical, and you have horizontal plane, and then you do the 3D interpolation using a formula that you can find in the literature. And what you get is essentially something that does not really look all that natural. And then the same antenna, they came to us with measured 3D, and the patterns here, again, you can use lower frequencies, or you can go to 2.4, and there you see how this all looks so very different, because those side lobes are now measured, and they look much more real than they were when we did interpolation. So what does it mean as far as the accuracy is concerned? Well, it means that when we take this antenna and when we put it against the is this not working now? Okay. And we put it against the floor. We put it against the inclined surface. What you see on the left is the approximation, the interpolated value of the antenna pattern. To the right, what you're seeing is the real deal, right? And you can see that the footprint that you see on that inclined surface is significant. It's significantly different than what you are seeing on the left. So what is the difference? This is the difference, and I'm going to help you interpret this. Everything that is blue, including the dark blue and this metallic blue, is bad. This green is not that big of a deal. The difference is half dB, but everything else is actually can be up to 5 dB or higher. So essentially, you have a very, very significant difference between those measured values and the approximated values. Now let's move on to capacity. And I'm just going to go very quickly through this because I only have about 7 minutes and I want to give you another demo using our tool. And these are listed capacity requirements. Factors that affect capacity are co-channel interference, airtime usage, the number of clients, and then within the number of clients, you have identified percentage of them connected at either of those two bands, percentage of active clients, percentage of clients with 1, 2, 3, and 4 streams, etc. Also ambient noise, which I mentioned, and the stadium is very important. And then also the maximum number of connected clients at AP. And then user profile. So what is with the user profile? What does it exactly mean? For each client, you should specify the period of activity, which can be 1, 2, 3, or 4 hours. Applications likely to be used, which is email, browsing, file transfer. The quantity of the usage and the file size in megabytes. And these specifications are called user profile. A user profile basically specifies how many megabytes of data a client is transmitting and receiving over a specified period of time. And different verticals have different user profiles. What we do is basically produce capacity heat maps. And for each AP, what we show is if AP can support given traffic, user traffic, or if it fails because there are too many connected users, or if it fails because the airtime usage is too high. And just to let you know, what we have done this essentially does not really differ all that much from the procedures of the capacity calculation that Andrew Vonage has in his Excel spreadsheet, except that we took a lot more granularity in here because we do three-dimensional signal prediction. And in our demo, what I'm going to show you is a basketball arena that has 10,000 clients. And each client is supposed to transfer 100 megabytes of data over 3 hours. We have 105 APs there. I would say about 58 of them are dual band and 47 are single band. And split between high and low band is 80-20. And target airtime usage is 80%. The question is, why do we have 105 APs? Well, you can do it two ways. You can basically say, okay, my ambient noise is, let's say, neg 80, and I need to have a signal-to-noise ratio of 20 to support file transfer. Therefore, my signal strength should be neg 60, and you go in and you put APs to have neg 60 almost everywhere, including, obviously, fading margin. Or you can say, well, you know, a good friend of mine heard at a conference from some guy that it is 100 clients per AP. Either way works. You have to start with something. And when you have the design, then you run your capacity calculation, capacity heat maps to see how much off you are. And let's take a look at that. So here, I'm going to show you 3D presentation of of basketball arena. So you can actually see where those APs are. Those little things that can barely see are APs that are above the area, above the seating area. And then I'm going to show you the capacity calculations first for 2.4. And there you see that as I said, there are 3 states. The first one is pass, and there are 2 fail states. The pass state is that basically you have the number of connected clients, and I'm going to move that over. So you can actually see what it says there, right? So you are going to, it is telling you that your airtime utilization is satisfactory or not. There you see 2 values, and I'm going to explain why you see 2 values. But bottom line is both of them are less than 80%, which is good because that was our target number. Then the number of connected clients is less than the maximum, which is 125. And then there are two other values, which is target throughput and throughput at 80%. There are a couple of failing areas. And if you go over there, you will see that it fails because of the airtime utilization. And airtime utilization is greater than 80%. And that's why it failed. It is about almost 100%. Now, you see two numbers. Why do you see two numbers? You see two numbers because this particular AP, like most of them, actually go over more than one level. This is what they call event level, but those APs actually transmit above to the level above. So when you see the report as to what the performance is, if you see two numbers, that means that the AP actually has signal recorded at more than one level. So this is how it looks in 3D. So basically, you can identify easily areas where you have problems, which are the red areas right here. And there, because we are failing on the air interface, and we are failing at actually 2.4 gigahertz, which we have fewer APs, then you can make a decision as to what to do next. Perhaps activate another 2.4 gigahertz AP. One last graph that I want to show you is a Cci graph at 2.4. You have a three-level structure with lots of open area. So you kind of assume that it's going to be very ugly, and it really is. And as you see, Cci goes all the way to 8. And this is how it looks like. I'm just going to move that a little bit. Yeah. So you have a Cci legend that goes all the way to the 8, and you see how Cci looks like in your stadium. And that's at 2.4. I'm not going to show you at 5, but at 5 it goes up to 3. It is much better looking. So that is another example of how congested 2.4 is, because we have only 3 channels and lots of open areas, and the Cci looks really bad. And accordingly, we are going to show what the map is of the average downlink data rate, and that is going to be also very, very low because of the very high Cci. I'm going to move that here. As you see, it starts at 51.2 kilobits per second, which is on the top, and doesn't get much better. So anyway, this is the end of my presentation. I'm about 1 minute and 15 seconds over. So it's a good time to stop this and open for questions.
Anyone? Questions?
Okay.
If not, if yes.
3D models, you mean the stadium? 3D model basically comes from the CAD files. And if you're asking me which basketball stadium that is, the answer is I don't know. I was given that by my engineers. I don't know which that stadium is. Okay, this was not done by our customer. This was done by us just to show what the software can do. We have not taken somebody else's work to present, if that's what you were asking. Mm-hmm.
Any other questions? Yes, sir.
Yeah, well, with the inclined floor, everything that has an inclined surface should use ray tracing. I'm not aware of anybody using COS31 to do the inclined surface. Where I showed the difference between 231 and ray tracing was in the area where it took the data, which was flat. And so that was essentially trying to be fair. But if you have inclined surface, I would basically say, yeah, go with ray tracing.
All right. Thank you very much, Vladan.
Thank you.